3 talks. So we'll be starting first with Professor Andreas Hagfeldt from Switzerland. He's the invited speaker for this session in nanotechnology and material science. Professor Andreas, he's a professor in physical chemistry and the dean of chemistry, he was the dean of the post of the chemistry at Uppsala University, as well as the director of the Center for Molecular Devices in Switzerland. But since September 2014, he moved to Institute Polytechnique of Lausanne in Switzerland. He obtained his PhD at Uppsala University in 1993 and was a postdoc with Professor Michael Karsozel 1993 at the Institute Polytechnique in Lausanne, in the same country. His research focuses on the field of mesoporous dye-sensitized solar cells, specifically physical chemical characterization of mesoporous electrodes for different type of optoelectronic devices. Professor Andreas has published more than 340 scientific papers that have received over 30,000 citations. With an H index of 88, and he has 8 patents applications. He was ranked number 46 on the list of the top 100 material scientists of the past decade by Times Higher Education. He is a member of the Royal Society of Sciences in Uppsala University, founded in 1710, and the Royal Swedish Academy of Engineering Sciences in Stockholm, Sweden. He is a visiting professor at Nanyang Technological University, Singapore, and a fellow professor at Sungkyunkwan University in South Korea. So please welcome Professor Andreas. Okay.
Thank you very much. It's an honor and pleasure to be here at King Abdulaziz University. So I thank the university very much for the very kind invitation to this conference, and for Dr. Abdullah for collaborations and for the invitation. So my talk today will be about half time about the dye-sensitized solar cell. Also quickly mention the status of where we are and what we think are the key directions for further improvement. Also briefly mention that from the dye-sensitized solar cell we have a very exciting development which is called perovskite solar cells, and I will overview a bit of our latest results also on that topic. This is our campus, and if you have the possibility to visit Europe, you are most welcome to EPFL and enjoy the Lake Geneva and the Alps. Before I go into more of the research, I would like to advertise the technology of these type of solar cells also for education. It's a very nice technology to give to high school students and even younger students to learn about chemistry, also to learn about nanomaterials, solar energy, and so on. Because without knowing anything in detail before, they can basically make their own dye-sensitized solar cell within a few hours. And then you can discuss with them the usefulness of solar energy and also chemistry and so on. So a few years back in Uppsala University in Sweden, we developed what we call the solar cell kit, and this is the box. We made 50 or 60 of them, which we then lent and borrowed to high schools all over the country of Sweden for exercise for about half a day. The ingredients are the contacts, the conducting glass here. We have a bottle with electrolytes, which is normally an iodide salt. We have a white powder of titanium dioxide, a pencil, scotch tape, and the exercise for the high school students is that they make their solar cell and then they should drive a simple display here in the calculator. So they should see that they can do that by using light, let's say. So this is the thing, and there is one ingredient missing here. If you used to work with dye-sensitized solar cell, you know that the dye itself is not included in here, and we encourage the students to find their own dye, so to speak. And of course we give them some tip. For example, they can try Swedish blueberries or strawberries and so on. So it's very natural in that sense. And then here is the procedure how to make a dye-sensitized cell. You have prepared a suspension of the nanoparticles of TiO2. You put a drop on the conducting glass. This is our contact for the anode. You have the scotch tape here, which makes a certain thickness of the TiO2 and also then mask for the electrical contact later. You have a heat step here where you sinter the nanoparticles together, so you form a porous, nanoporous layer of the titanium dioxide film. And here is where the fun part of the lab starts, where the students have to find their own dye and put it into suspension and so on. And as I said, in Sweden we of course encourage Swedish berries like blueberries, but I know a lab in United Kingdom where they of course use tea, so you can take your national sort of drink, fruit or whatever to try here. I even saw a student proudly saying that he had tested his own blood in making a solar cell, so you can even do that as a sensitizer. Then your photo anode is ready, and you need a cathode also, and in a simple lab we use graphite from the pencil here, and then the two electrodes are clamped together. You fill up the space between the electrodes with iodide containing electrolyte, and then you put the contacts, and for the lab they need to realize that to get 1.5 volt to drive the calculator here, they need to connect in series 3 or 4 cells. So that they can do, and then you can discuss with them how it works and how photosynthesis works and so on. So I think it's a very nice also aspect of the research we are doing to create interest from let's say young people. A little bit then on the history. This is, as far as I know, the first example of a dye-sensitized system. It's here in German by James Moser, 1887. And the driver, the motivation came from photography. And what James Moser here wanted to do was to make photography with colors, let's say. So he used the silver halides and then put a natural dye, erythrosine dye, on the silver halide and could obtain with visible light, if you can read it here, about 1/4 of a volt, he mentions. So he could see an electrical effect on dye molecules on a semiconductor. And also very nice, this is actually the complete paper, so it's very very concentrated, very efficient. So I think it's a nice example of that. And then it took maybe almost 100 years before people started to understand what is actually happening in a dye-sensitized system, and it's a lot thanks to Heinz Gierischer and his group with Helmut Tribuch at the end of the 60s presented the mechanism that we have a semiconductor, the valence band, conduction band. We have a dye anchored to the surface, and you excite the dye from the ground state to the excited state, and the electron is injected, and you can then measure a voltage and a current in an electrochemical cell. Then it took another 20-30 years before we saw a real practical possibility to use these electrodes. And this, I think, is a picture taken by one of the audience, Professor Bisquer. It's from 2012, so thank you, Juan. It's in Uppsala, and it is a famous paper by Brian O'Regan here, and of course Professor Michael Gretzel, presenting a real jump in efficiency from something less than 1% overall efficiency to 10 times higher, about 7% efficiency, and created a lot of interest, of course, for application, but also fundamentally because the solar cell they presented was based on a high surface area, nanoporous system, and according to textbook at the time, let's say now 1991, this was a way of how you should not make a solar cell. To use surfaces would, in principle, according to textbook, lead to losses, recombination losses. So this was very surprising, and even so that people even didn't believe in it in the beginning. A bit of the schematic, how it works. We have the contact here, the transparent conducting oxide, normally fluorine tin oxide, the TiO2 particles, about 10 micrometer thick quite often, 50-60% porosity, the size of the particles 20 to 30 nanometers. You have the dye preferably on a monolayer on the surface, and an electrolyte impregnating the pore structure. And I would say state-of-the-art system from 91 and about 20 years has been this type of mesoporous TiO2 iodide electrolyte, and this is the famous dye also prepared by Professor Naseruddin, also in the audience, and will give a talk tomorrow. It's called the N719 dye, Naseruddin's 719 dye. It's a ruthenium complex with piperidinium ligands. You have the carboxylic groups which are attached to the surface chemically, and these ligands turned out also to be very successful to redshift the absorption and also involved in the electron transfer to regenerate the dye. So the principle is that you come in with photons through the contact, you excite the dye molecule, the electron is injected, as we say, to the TiO2, it is transported by diffusion normally through all these particle layers to the contact, and then makes electrical work, goes to the cathode, reduces the triiodide to iodide, and regenerate the dye by bringing the electron back to the oxidized dye, and then we close the circuit. So this is how it works and so on. And we could also, with time, not in the beginning, try to understand why this solar cell work. As I said, one in principle should avoid surfaces, but here TiO2 and the electrons in TiO2 is not reacting very efficiently with the electrolyte, so it's okay to use this one. Although to change electrolyte turned out to be very difficult. We could also understand that the dye molecule itself could separate the charges because the orbital architecture of the dye is such that when we excite the electron to the excited state, we populate the pi star orbital of the carboxylic group, and that's exactly where we want the electron to be because that is where we have the TiO2 surface. And the remaining hole here is very much located on the sulfur atom on the ligands. So when we do the excitation, the electron moves to the TiO2 surface, the holes moves out to the electrolyte, and in that way the dye can separate the charge, and then the electron can be transported through a diffusion mechanism. And also Professor Bisquer had described in more detail how the transport works with the trapping, detrapping mechanism. So that's the overall picture. In terms of applications, we start to see several prototypes and nice colorful applications. Let's say this is an example where we have a very artistic solar cell made by the Sony company, using different colors, transparencies and so on, and making like an art basically. This is what we see when we go through the Geneva airport all the time. It's a company called G2E in Switzerland. You can think about doing it on flexible electronics, flexible substrates, lightweight, and integrate them into backpacks to recharge batteries. I was involved with the BASF company some years back in Germany, where they made this car together with Daimler-Benz as a prototype. And in Lausanne also we have a quite new congress center where about 200 square meters of these modules of dye-sensitized cells are used as a facade material in a way. So we do start to see demonstrators and different applications. And if I should summarize the status of the industrial side of the technology, I would say that the technology as it is mature for consumer electronics. It's better than conventional silicon cells, and some products are starting to be sold also, like recharging keyboard for iPads and so on. This is more a question of marketing, I would say. Where is the market for such products? And maybe with concepts like the Internet of Things, with a lot of sensors being necessary, there can be a substantial market for indoor application. If we go for more advanced applications for these dye cells, like buildings, I said we see some demonstrators. This is from the inside of the Swiss Tech Congress Center in Lausanne. This is then the dye cell glass facade. There have been some other buildings also demonstrated last year and this year. So I would say that we start to see some demonstrators coming up. Not a real market, of course, but it's exposed. If I would take this dye-sensitized cell and see can we compete on large scale with the silicon cells which are produced in large scale, manufactured mainly in China, I would say that no, we are not there with the technology. We need 1 or 2 or maybe 3 more breakthroughs to really be able to compete in terms of efficiency and also stability. So here, of course, is where we are as an academic research group looking into possibilities. How can we then now make higher efficiency and also besides these kind of initial applications also think about it for large scale use. So I will talk about this the coming 5 minutes or so, where we think is the key direction to increase the efficiency. It started some years back, and the question was where in the conventional dye-sensitized cell, based on the ruthenium complex, the iodide electrolyte, TiO2, is the main drop, internal potential drop in the cell. And it was nothing particularly strange. We know it almost from the start in the 90s that we do have a large internal loss in potential when we take the electron from the electrolyte to the oxidized dye. This is what we call regeneration of the dye. There we lose in the iodide system about 0.6, 0.7 volts. The question was, why do we need so much potential in that step? Can we reduce it and in that way gaining more efficiency? And in principle you can do that in 2 ways. Either you take and change the dye, so you move your HOMO level of the dye, the ground state, up here, so to minimize the potential drop. And if you do that and keeping this level constant, you would redshift the dye and you hope for a higher current, let's say. But the potential is given by the Fermi level of the TiO2 and the redox potential of electrolyte. So by moving the dye state up here, you hope for a constant voltage but higher current. Now it turns out that with the iodide system it's not so easy to reduce this potential drop so much. You will lose in regeneration kinetics. The other option is to move the redox potential more positive, as we say, in this direction, and in that sense gain a higher voltage of the cell. This also turned out to be very difficult because what you do if you change the redox system is that for other system than iodide, you open up a recombination process from electrons in TiO2 out to the electrolyte. This is slow for triiodide, but normally very fast for any other system. So going back to the study of our iodide, the question was, do we need 0.67 volts? And we think we actually need quite a high potential drop here, because the iodide system is not a simple redox. It's not a one electron shuttle. We do create bonds like iodide to triiodide, and therefore it's a two-electron process, and we need to have some intermediate steps here. And that is the question we addressed. And our conclusion after some studies was that the mechanism for the regeneration is that the iodide brings the electron back to the dye, you form an iodine radical, and that redox potential is the crucial one for the driving force to regenerate the dye here. And that is about 0.3, 0.4 volts higher than the dye state. And that was our conclusion, saying that the driving force in the system to regenerate the dye is actually not 0.7, it's 0.3, 0.4, and perhaps we can't do so much more with the iodide system. The rest we need to use to create the I3 minus system. So hypothetically we said that to improve the cell, another quantum jump would be to replace the iodide electrolyte with something else to make this potential more positive, but at the same time we knew that the problem is that we may open up a recombination process, losing electrons from the TiO2 to the electrolyte. Then we had, I must say, a bit of luck, because we were trying different things. We were developing with Professor Lee Cheng-sun in Stockholm these kind of organic dye molecules. We call this dye D35. Erik Gabrielsson was the one who made it. It's a triarylamine unit. We have the anchoring here, as you see. The thing with this dye was that we brought in alkoxy groups on the side here as a side group. The reason in our mind was that we could avoid dye aggregates. The problem with organic dyes is that they aggregate, and that's not good for the charge transfer to the TiO2. This was successful. They do not aggregate because of these groups, but we had an unexpected, I would say, luck here, and that was that with these alkoxy groups we can also passivate the recombination process. As I said, normally we are worried about electrons in TiO2 reacting with the electrolyte in such a process, but with these alkoxy ligands here we could stop that and passivate that reaction, and that was not intentional, but we had a piece of luck. And then our first choice to try something else than iodide was to use this cobalt 2+3+ complex. It's a bipyridinium complex, and very early on we got nice efficiency with this one, and we had presented 2010 about 7% efficiency with this system, which was the highest at the time for something else than the iodide triiodide electrolyte. Then this created a lot of interest, and EPFL and Professor Michael Gretzel, I remember, called me once and he said, well, you are right with the cobalt, now we have 9% efficiency, and it also increased, and the best results at EPFL since 2 years back is with this zinc porphyrin dye molecule, and I know that Dr. Zakirudin will talk a bit more on the dye cells from EPFL tomorrow, but just to point out here that you also see the alkoxy groups on the side here following the design to passivate the recombination process, and the result here is done with the cobalt complex I just showed you at 13% efficiency, and you can make these nicely green colors and so on. So this has been state of the art until about a month ago, when we saw a new paper coming up from Japan. It's the Adeka company. They have made a co-sensitized system with an organic dye and also one of our dye from Sweden, the leg 4 dye here. So these two together with the cobalt phenanthroline cobalt complex is the published record of dye sensitized cells today at 14.3%. So this is where we are at the moment. Now the question is, can we still think about further improvement? And the latest direction we take comes from an understanding of what is now with the cobalt complex the driving force we need to regenerate the dye. I said it was 0.7 with iodide, and here we can nicely study what we need in terms of potential driving force to the dye by tuning the different cobalt complexes here, which we did from Uppsala in collaboration with EPFL. And I think we made about 12 different cobalt complexes with different redox potentials. And what you can do then is a classical electrotransfer theory process. You can study how much the potential difference, delta G, free energy you have between the electrolyte and the dye, and then measure how fast the kinetic is, how fast this process go, and then find the optimum, let's say, where, or the driving force you need for efficient regeneration. And to make a long story short, we are down to about 0.4 volt needed in the gap here to regenerate the dye efficiently. So we took it from iodide 0.7 volt with cobalt to 0.4, and the question is, can we do even better? To summarize, I would say what we are looking for to make higher efficiency than perhaps 15%. I would say ideally if we can go down to driving force of 0.2 volt, that would be very nice, let's say. Then we can gain even higher voltage. And of course we need some other things. We still need to worry about recombination processes and so on. I will tell you that we think now that we have one possibility with a copper complex instead of cobalt to regenerate efficiently. So this is a work this is actually not published yet, the liquid results. It's a postdoc of mine, Marina Freitag in Uppsala, started and continues now at EPFL. It's a copper phenanthroline redox system, the organic dye, and we have similar efficiency as the cobalt system, about 7%, so that's good news. We have very high voltage with the copper phenanthroline, higher than the cobalt, it's about 1 volt. So that indicates to us that we can have a positive redox potential, and this is very positive. The regeneration now we can use is exactly the 0.2 volt we are looking for. We can regenerate the dye with the driving force of only 0.2 volt and 100% regeneration. So here now we think we have reached a target redox system and dye where we can explore further. So this is where we are at the moment. We are now trying different dye molecules to see if we can benefit from this very efficient dye regeneration. We had another surprise just to finish the dye sensitized talk, and that is that normally when we work with this liquid electrolyte in a dye cell, of course one can imagine that there is problem with leakage of the electrolyte. It's a liquid, and it can, if the sealing technology is not good enough, we can have evaporation problems of the solvent. And what normally happens if we have a cell which is dried out, we have leakage problem, and it's dried basically, is that they are dead. They don't work anymore. With this copper phenanthroline system, that happened. We didn't have a good sealing in Uppsala, so after 2 months the cells were completely dried out. For some reason the technician in the lab said, I will measure them anyway, measured them, and they were even higher in efficiency than the liquid cell. Very strange, and we still don't know why that is so, but it's a very interesting and surprising effect. So from 7% with the liquid, we are at 8% with this kind of solid state system with a dried out cell of copper complexes. So this may also then facilitate practically easier system to work with. So this is something exciting, and that's what we are working with for dye sensitized cell at the moment. I will then finish up to say that we have seen the versatility of the system is that we can do chemistry. So we can replace the dye molecule with inorganic light absorbers, pigments, quantum dots. And also in the audience is the one who made the first quantum dot sensitized cell, Professor Horst Weller, in the early 90s or even late 80s. And you can use lead sulfide, cadmium sulfide, and so on to basically replace the dye. You can have dye molecules in the electrolyte to harvest light and by energy transfer take advantage. You can replace, as I said, the liquid electrolyte with the solid hole conductor, and the classical one is called spirometad here. It's an organic hole conductor. We can think about tandem cells, making the cathode also visible, active for light, and so on. If you now combine the time here to look into replacement of dyes with inorganic material, like a perovskite crystal, if you combine that with the solid hole conductor, we came up with the breakthrough, the latest breakthrough in photovoltaics, and that is called the perovskite cells. That started with this colleague and friend, Professor Tom Tomi Asaka from Japan, and he started as a hobby to look into possibilities to replace dyes with a perovskite material, an organic, inorganic perovskite. Early 2000, I think, with a student, it was not so successful, so he tried. He started to talk about it in conferences 2006, as far as I know, saying that he did some perovskite with about 2-3% efficiency, but he had to be very quick to run to the lab to measure the efficiency, because they were stable not for more than about 10 minutes, just to have time to do the measurements, and then they were dissolved in the liquid electrolyte. So that was the problem, and finally he published a paper in 2009 describing the perovskite at 3-4% efficiency. Because he's also a keen violin player and made a publication in something called the Strad here in some years back. And I think the two hobbies here, one, I think just a few years ago, I think the citations of these two papers were maybe quite equal. Now one of the papers have got a lot of more citations, of course. The breakthrough came then, two parallel independent work. Henry Snaith at Oxford contacted Tomi Asaka to ask if we could work on solid-state Hall conductors with the perovskite, and asked for the recipe. And Namgye Park contacted EPFL to ask the same thing, basically. And then in parallel in 2012 it was published about 10% efficiency using perovskite and the solid-state Hall conductor. And that has really created a huge amount of interest for the moment. And I think we had 2012 perhaps 10-15 papers published after this. This year I'm sure there are more than 1,000 papers published on the perovskite cell. So it's really a very encouraging results, and going from 3% efficiency in Miyazaka's, this was 10, today the world record is 20.1% certified, let's say. The best results, and I will now not go through so much of more to focus on our own recent results. Our best results at EPFL at the moment is based on a mixed perovskite. We mix the classical one is methylammonium lead triiodide, but here you see we start to mix in some bromide. It's tuning the band gap a little bit, and I think also makes the halide a bit more stable. We have lead, and then we mix the organic part, which is methylammonium, and the formadinium cation is also mixed to a little bit tune the gap, and also to change or to optimize the morphology of the perovskite. So this was presented from the EPFL group in Angewandte, and the Professor Seok from Korea has then the certified world record of 20.1% using this kind of mixed perovskite. And here is our most recent results. It's now accepted in Science Advances since a week ago. It's 20.8% in the lab and certified at 19.9% efficiency. So we do this mixed perovskite. We have still a thin layer of mesoporous TiO2. The Spiro Ometad is the Hall conductor used here. So we have, here is the FTO, we have a blocking layer of TiO2 by spray pyrolysis. We have a quite thin layer of the nanoparticles of TiO2, about 200 nanometers. That includes perovskite in the pores, but most of the perovskite is in the compact, what we call the capping layer on top, about 400 nanometers. The Hall conductor, and then the gold as a contact. So this is optimized with the recipe of the composition of the mixed perovskite, and we do see also that we need a little bit of excess of lead iodide. That helps, and we think we have about an excess of lead iodide of about 3% to 8% in the total perovskite structure. We can tell that the lead iodide excess is beneficial. It decreases recombination processes that we know. We see an increased photovoltage with this lead iodide excess. We see higher luminescence, so the emittive recombination increases. So it suppresses non-radiative recombination. That we can tell. Then in the details where this lead iodide is in the film, if it's sort of around grain boundaries of perovskite or at interfaces, we are not really sure where we have the lead iodide excess. And exactly where the recombination process is decreasing, we have to look further, let's say. So it's more questions coming up, but we can definitely say that it's beneficent with this excess decreasing recombination. So that's the latest news. I can show you then okay, yeah. This is a postdoc at EPFL, Dongxin Bi, who's been the main driver about optimizing this composition to 20.8%. Also in the field, one discusses a lot that you have what we call the hysteresis effect. It means that the efficiency measured may depend on which direction you do the measurements of this IV curve. If you go from short circuit to open circuit, or if you do scan in the other direction, it may look very different. But in this case, they are very similar actually. So we don't see this problem with the mixed perovskites. Of course, then we were excited. We went to do the certification, and we were of course eager to see if we could compete with the 20.1 from Professor Zook, and we obtained 19.9%, so very close. But the lab record we have is 20.8%. So that's where we are with these cells. This is a bit complex diagram, but it shows you that the green one is the focus on, it's the luminescence at an applied potential. So if we applied 1.5 volt here, we have about an external quantum yield of electroluminescence of about 0.5%. And that is sensationally high, actually. This is for organic solar cells, normally 10 to the minus 6 or something. So to have 0.5% we think is a record for this kind of hybrid organic, inorganic solar cells. It also means that this material is also explored for light-emitting diodes and so on. I'm at the end. We can of course also now, as you saw from the picture, we had a very thin layer of the mesoscopic TiO2, which we can of course say is useful because we can inject electrons from perovskite to TiO2 like a dye-sensitized cell. On the other hand, most of the perovskite in the film is in a compact layer, so we can ask, can we simply just make a planar perovskite layer and then use let's say a contact FTO with some blocking layer, so we accept electrons but block the holes to react. TiO2 is the obvious choice, of course. Have a compact layer of perovskite without any nanoparticles, and then the whole conductor and the contact. This is a normal thin film solar cell like CIGS or cadmium telluride and so on. This has of course been tried with moderate success, I would say. It's around 13-14% normally, with fairly problematic with the hysteresis. We had also here a project with my postdoc Juan Pablo and the PhD student Ludmila, who works with ALD deposition. And for some fundamental reasons, we wanted to try different contact layers. TiO2, as I said, is the obvious one, but we also wanted to see if we change the material to tin oxide, niobium oxide, what does it make to the cell, to understand. And the success we had with this planar structure was to change to tin oxide. So TiO2 as the sort of traditional contact, we had fairly poor efficiency. This is the IV curve with the voltage, a strange IV curve with a big hysteresis and not very useful. Changing to tin oxide as the material, we have very nice results, about 18% efficiency and very low hysteresis. And the best voltage we have in the lab is 1.19 volt with the tin oxide actually. The reason we think TiO2 does not work with this ALD deposition is that the conduction band of TiO2 is too high compared to the perovskite, so we cannot inject into the TiO2, whereas tin oxide seems to be ideally matched with ALD to the perovskite and get high voltage. This is the what we can explain it with, but there could be of course further explanation, and we have a collaboration with Professor Bisquer here who seems to have some interesting data on that topic. So it's more to be explored here. This cell is done at moderate temperature, so we can think about using them for flexible substrates. We don't need more than, let's say, 150 degrees Celsius. One initiative was to collaborate with a group in Berlin who works with silicon solar cells, and that was to make a monolithic tandem cell. So you basically take a silicon cell, add on the layers of tin oxide, perovskite, and then make a tandem cell device. And the idea here is, of course, that you can get higher efficiency than a one-cell absorber. So ideally here we can think about theoretical efficiencies of higher than 30%. So as a proof of concept, we have 18% efficiency with a monolithic tandem cell, which I think is the highest published on this kind of monolithic tandem cells. We have another tandem configuration done with Professor Segawa in Tokyo. That is to take a dye-sensitized cell with our new black dye, they call DX3, as a top cell. It has an infrared absorption. You combine that with a perovskite solar cell, and then we do it not as nice as a monolithic. We have a split cell, so we take a mirror to split part of the spectrum to the dye cell and part of the spectrum to the perovskite. And as a proof of concept, we have 21.5% just published in Nature Communication. To summary, the direction, I think, from an applied point of view for dye cells is to use the design principles. We can think about different colors, transparencies, really nicely integrate them into products like windows, backpacks, and so on. Still, I think we have a potential to improve efficiency. And I said the direction we think is to still work on the regeneration of the dye. We think we have a very nice possibility with copper redox systems at the moment. There is an emerging field I didn't talk about, but that concerns not to do electricity, but to make hydrogen and oxygen with this kind of molecular catalyst and molecular light absorbers. It's a growing research field. For the perovskite solar cells, it's a big discussion if we should think about competing with silicon or perhaps rather join silicon cells in tandem cells. And they can also be used because of high voltage to drive water splitting systems. With that, I think the PIs, so we are three lab groups in DPFL. Professor Michael Gretzel is heading the LPI, and Professor Nasiruddin is leading his group. And this is my group with postdocs and PhD students. And some of the work was done originally in Uppsala University with Gerrit Borslu and Lee Chang-sun. So thank you very much for your attention.
Thank you so much, Professor Andreas, for this wonderful things about the new technology and promising technology in solar cell, especially the perovskite and the dye synthesized solar cell. So we will open now the stage for questions. Any question from the audience? Yeah.
Yeah.
Maybe even 200 would be sufficient.
For cobalt, yeah.
For cobalt.
Could be, yeah, in the mic. So the question is, with the cobalt complex, I said that we had efficient regeneration at 0.4 volts, but lower than that. For these organic dyes we tested, we could not regenerate efficiently. So but you're right. I mean, we always have to be careful not to generalize too much. It always depends which dye you compare with and so on. So of course I think also with cobalt complexes there could be possibilities if you can have let's say some kind of constructive attraction between the redox cobalt and the dye to speed up the kinetics there. And I think one reason maybe for the higher driving force for cobalt as we measure has to do with reorganization energy, where I think the copper complex we have has a less reorganization energy than the cobalt. But this is speculative, of course. But you're right. I mean, there's still many things to do with cobalt too.
Yeah, thank you.
Sure about that.
Any question?
So, do you know what is new about this 14% dye solar cell? What was the improvement of the dyes. Are you familiar with this?
Yes, there is a good absorption spectrum. I mean, they take advantage of the co-sensitization, so they have a good current. It's a little bit not straightforward to reproduce, maybe, because they have a lot of processing of the TiO2 films, which I think is not so easy to follow. So they have a they improve a little bit higher current, maybe than the 13%, a little bit higher voltage too, which may come from optimizing the TiO2 surface and so on. And the copper phenanthroline also gives a little bit higher voltage than the copper cobalt 3sp pyridinium system. It's on the margin, let's say. Everything is a little bit better. I think one thing, if I discussed at least with Garrett Boschlo, who read very carefully, he thinks also, it seems in the experimental section, that this is not a sealed cell. They have an open electrolyte cell, which makes it even more a bit tricky to reproduce, maybe. So we have to see where this goes, but it's the highest published result so far.
Okay, final question, please. Okay. So, thank you again, Professor.
Thank you.
And we'll be moving now to the next presentation. Professor Wardi Sharif Zehran from Tunisia. Okay. If he's not here.
Do you have female section? Anyone in the female section? I'm not sure, because we couldn't receive anything from them. So
There is the last two.
oh, the last one. Okay, that's fine. Okay. I'll go to the next one. The Zahoor Hussein Farouqi. Zari. Right. So I think we'll finish by Rubina Begum, a PhD student. Rubina Begum. I'm not sure if he or she PhD student. She, yeah, Rubina Begum, a PhD student. I'm not sure if the microphone in the female section is working. Yeah, because there is no response. So if you ask them just to connect us with them. Nothing? Connected?
Maybe no one is there.
No one there. All right. So I think we'll finish off by the. If there is any comments on Professor Andreas' presentation, especially when we're talking about renewable energy technology, it's one of the, I would say, promising thing nowadays in the market. So if there is any question for Professor, or you want to add anything, okay? Would you please, the mic, please? Can you bring the mic here? So we'll have another 10 minutes. Then we'll go to the lunch. Okay.
Thank you, Professor. I'd like to ask you about the stability of perovskite solar cell.
Yeah.
How can we approach enhancing the stability? For example, we are stuck by methyl ammonium, lead iodide, bromide, or whatever. How can we change the group or adding aromatic moiety or whatever? does it have some effect on the stability, or someone did this work before?
Yes, I can, and maybe others, since it's a more general discussion, we could fill in and so on. So from, to start with, I would think that with the extremely exciting improvement of efficiency, we must start to see some saturation at the efficiency. So the big question mark is, of course, stability for perovskite, and I would say that it still needs a lot of more research to be done and see how it is. There are many reasons why it's not stable. We do see that halides can be mobile. We have an organic part which is freely rotating and can in principle evaporate and so on. And then we have hole conductor interfaces and so on. The experience we have is that, for example, there are some, I would say, encouraging stability tests being presented. The most encouraging one is to simply take away the hole conductor spiro and replace it with a carbon contact, for example. There people have shown from EPFL and from Dr. Hongwei Han in Wuhan University that you can have 1,000 hours stable cells at 45 degrees Celsius, I think was the measurement, continuous irradiation. We have seen at EPFL that the hole conductor material can improve stability. We have one example where, and I think maybe Professor Naseruddin will maybe mention that tomorrow, I don't know, but there is, if we replace the hole conductor compared to spiro, we do see an improved stability. For example, it's a silicon-based hole conductor. So it seems maybe one conclusion is that the spiro is a weak component in terms of stability. Therefore, one direction would be to find perhaps inorganic collector materials completely, like the carbon or something else. There is a recent paper in Science where they have used lithium-doped nickel oxide hole acceptor, which also shows some promising stability testing. So this is to be explored, I would say. But as I said, there are reasons to look into this very carefully. And I think from an industrial point of view, I mean, of course they observe what is going on, but I think they are a bit careful to jump into it completely without seeing also stability. And this, as I said, there is stability test at continuous illumination, but to really go up to 85 degrees, which is the protocol for silicon, that will be, I'm sure, challenging. But maybe some others can fill in with the experience. But my view is that it's much to be done. There are some encouraging results pointing to problems with spiro hole conductors and so on.
I think we've heard something from the female section.
Yeah. Is there anyone in the female section? Hello? Okay, there's no one there.
Yes.
Yeah, okay. Any question?
No question.
Any question?
Yeah.
No.
No question.
All right, okay. Thank you. Okay, so I think we can finish the session. And
The lady there?
Mona speaker,
No,
can you speak now?
Speaker is there?
yeah, please, is Rubina Begum is around? She's a PhD student and she's supposed to have a presentation.
She belongs from Pakistan.
Yeah, she's from Pakistan. And she's with the code NAM 29. The nanotechnology and materials 29 is supposed to be in the third presentation of this session. Rubina Begum.
She didn't come.
She didn't.
She didn't come.
Oh, she hasn't arrived. Okay. So thank you again, and we'll have now lunch. I will be back inshallah in the afternoon. Thank you.
Lunch. When you do presentation, use this one.
Patient to be here,
and also for the putting together a wonderful program. I really enjoy it. So today I would like to share with you the current and progress and challenges of solution process organic solar cell. So this is the outline of my talk. So first I will give a brief motivation why we and also other research group in the world work on solar cell in general. And then I will introduce the concept of both heterojunction organic solar cells. And then I will discuss the relationship between film morphology, charge generation, charge transport, recombination, and the device performance. And so I will also briefly discuss losses, different type of losses in organic solar cell and factors that may affect the device characteristic. And so the motivation behind our work has something to do with the future energy challenge. So the current global energy consumption is 16 terawatt. Projected consumption in 2050 will be about 28 terawatt, and this is due to population and also economic growth. And so to cap carbon dioxide at the 550 ppm, which is twice the pre-industrial level, most of this additional energy must come from carbon-free sources. And if we look around us, there are more than one type of carbon-free sources, but solar energy is by far the largest carbon-free energy source, especially in Saudi Arabia, where you actually have the sun all year round. So the question here is how can we harvest the energy economically? And some of you may say, well, we can actually buy silicon solar cells, so we do not have to worry about a future energy challenge. And yes, the answer is you can actually buy quite efficient silicon solar cells. The commercial module you buy and put on your rooftop, they can run about 14 to 15% efficiency, but they're quite heavy, fragile, and they used to be expensive, but still relatively expensive now. But if you look at other type of solar cell technology, we already heard that this morning an invited talk on dye-sensitized solar cell and also on perovskite solar cell that making a lot of progress. And I'm working on the organic solar cell, and I just want to point out the picture on the right. So that's the first commercial product of organic solar cell produced by Mitsubishi Chemical Corporation in Japan. And the product actually, the way you can see, is semi-transparent and at very low cost for installation because you just fabricate the window screen, you can actually hang it up. And so currently you can buy in Japan, but we cannot actually buy in the US or in Europe yet, and they hope to be available to the US market in the near future. And so it's quite exciting to see the type of technology in the commercial product. And so you can see there are a variety of applications that, for example, organic solar cell may have the advantages over silicon solar cell. For example, if you need something lightweight and flexible and also semi-transparent, where you can coat window on building or glass building with semi-transparent, that's the type of technology that you can do with dye-sensitized solar cell or organic solar cells. And so this slide shows the research progress of different types of solar cell technology, and I would like to get your attention to the bottom right of the graph. And you can see there are a variety type of solar cell technology, including dye-sensitized and also organic solar cell. Organic solar cell, you can also see they are basically evaporated small molecule and also solution process. And so the efficiency has increased rapidly in the past 5 years or so. So right now you can actually see the lab prototype, they have about 12% or so. And for sure this is still lower than the dye-sensitized solar cell reported this morning, or perovskite solar cell. But what I've known that, for example, organic solar cell, the stability up to the point is quite good. And so with that, I would like to explain to you briefly how organic solar cell work, especially the concept of bulk heterojunction solar cell. So in this type of solar cell, you have a powder or polymer or small molecule donor, and you blend in with the fullerene derivative at electron acceptor, and you dissolve the compound in organic solvent, and then you make a thin film, and then about 100 to 200 nanometer thick. And when you shine light to that, the material absorbs light and create the excited state, which also known as exciton. Physicists like to call it exciton, but for chemistry language, you call excited state. And so basically, this exciton can diffuse along the polymer chain to the donor-acceptor interface. And when they see the acceptor interface, they actually can do ultra-fast electron transfer. And the process happens at about 50 femtosecond or so. And then after that, the hole remain on the polymer backbone, and the electron hopping from one fullerene to the next to go to the appropriate electrode where they are being collected. And as you can see here, so this in this type of solar cell devices, the performance of the solar cell depends strongly on the film morphology. So what do I mean by the film morphology? So you start with molecule and how they actually arrange at molecular level, and they organize the cell assembly to form a solid state with nanoscale. And then when you have donor mixing with the acceptor, they actually phase separated, and they form a nanoscale domain, and then they form bulk heterojunction with percolation pathway to transport charge. And you can see here, since the morphology really requires us to understand at different length scale, and I believe that it's very similar also in this issue that you see with perovskite solar cell, the morphology also important there, and the same with dye-sensitized solar cell. And how do we actually make organic solar cell? So in the lab, we do not make the large area solar cell. We make a prototype which is quite small. And as you can see here, we start with the donor and acceptor powder. We dissolve them in organic solvent, and then we actually deposit them on a few drops onto the ITO coated glass substrate. And so when you spin, the solution spread out, and to form thin film, the solvent evaporated and yield thin film. And the thickness of the film can be determined by the solvent concentration, then how fast you spin, and that can use to control the film thickness. And after we deposit the organic semiconductor solution, and then we transfer our film into the vacuum chamber, and that's where we thermally deposit aluminum cathode. And the device schematic drawing I show in the bottom right, and then on the left, bottom left, an actual photograph of the organic solar cell and prepared with different donor material. And you can see here we can change the color of the solar cell from green to blue to red, depending on the donor that we use. And after we actually make the device, and this is how we characterize the device. So we measure the current as a function of the voltage. And the blue curve is basically we measure the current voltage in the dark. And then after that, we illuminate light to the device, and we collect the photocurrent, which is the red curve. And you can see the device efficiency determined by a couple parameters, the fill factor, and also the open circuit voltage. I mean the maximum voltage generated by your device at zero current. And also depend on the short circuit current, which is the maximum photocurrent generated by your device under zero applied bias. And of course, if you shine more intense light into the device, you have higher efficiency compared to weak illumination. And so another type of data that we also collect in addition to the current voltage curve is incident photon to collected electron. Or another name for that in the literature they call external quantum efficiency. So what exactly the EQE? So basically you shine light to that, you just measure the number of electrons collected per incident photon. And basically you shine monochromatic light to your device and you measure the photocurrent at each wavelength. And if you integrate the area under the curve of your EQE, it should give you the same number of the short circuit current that you do the measurement for the current voltage curve. So what kind of information that you can gain by doing the EQE measurement? So basically, it's another way for you to double check your device measurement using current voltage curve, which you require to know the exact electrode area. And then if you have two components in your system, it tells you which component of the Bohr heterojunction is effectively converting photon into current. And it also tells you what portion of the solar spectrum is being collected. And so the type of research in our group that we work closely with synthetic chemists, where synthetic chemists design the material, they synthesize the material. We take the material, we learn how to process them to make thin film, and then we perform both nanoscale and bulk measurement, and then we evaluate the device performance. We also have the effort to understand the device physics. So if a device works or doesn't work, we would like to understand why. And we would like to establish structure function property relationship in organic solar cell and then provide the information to synthetic team so that they can synthesize the next generation of the material with better performance. And so now I will focus on, we study many different compounds over the past 12 years, but I would like today to focus on one compound that's synthesized, designed and synthesized by Guy Bazin at UCSB. And so this type of compound based on donor, different type of building block that they put together. As you can see here, they have donor 1, which is highlighted in blue, and then they have electron acceptor unit, highlighted in red, and you also have the donor 2, which is bridging the center of the 2 acceptor. And when you design a material, usually they take into account variety criteria to design material for organic solar cell. For example, you want the material contains strong absorbing chromophore, so it can absorb more photon. And then also have strong molecular order, and I will explain throughout my talk why this is important. Because when you have a strong molecular order, it's easier to transport charge from one molecule to the next. And then you also need the material that have low band gap and deep HOMO so that you can absorb more solar spectrum. And then you want also the solution process, because a lot of time we want low cost fabrication, and using solution process you can use, for example, roll-to-roll coating method, just like you print newspaper, or you can put your solution into inkjet printer and you can print out any pattern, size, shape. And then for the application in solar devices, you also want your material have to be thermo, photo, electrochemically stable. And so over the years, the Bazin group have designed and synthesized a number of molecules, and we have studied them. For example, if you go from the left-hand side of the screen, you go from top to bottom, basically they increase the conjugation length in that molecule. And if you look at the series of molecules on the right-hand side of the slide, and basically they keep the size of the molecule the same, but they actually change the end unit. And if you look at the 2 molecules in the bottom of the slide, basically the length of the molecule are the same, but they change the functional group attached to the molecule. So you can use branched out side group, or you can use linear side chain, because those can impact the way the molecule pack at molecular level, and therefore impact the film morphology. And so now I will focus on just this one molecule. And so first, make it by Guy Bazin in 2011. And so you can see here, this is the absorption of the protein T1 molecule. The blue one is the absorption in solution, and then the red curve is absorption in the film. And you can go from solution to the film when there are no more solvent. The molecule actually have a strong interaction between molecule, and you can see the absorption actually broaden, and you see that vibronic structure appear, the peak that appear on the right-hand side of that plot. And usually that signature of the film very ordered. And now we actually blend the film molecule into PCB 70BM. So PC70BM will be electron acceptor and the T1 will be electron donor. And so from the energy point of view, you can see that the T1, which is the orange, have the HOMO level and it's higher than actually the LUMO level 3.34, higher than the LUMO level of PC70BM. So there is a driving force for electron to transfer from T1 to the PC70BM. And then to complete the device, we actually make the cathode with calcium and aluminum. And you can see this is the device characteristic of the T1 blending with PC70BM. The device fabrication in two different methods. One, we use ADCAS. It means we make the film, we make the complete device. We call ADCAS. The other case is the green curve, where we actually add in the solution a very small amount of additive called 0.4% by volume. Diiodo octane. So this is the high boiling point solvent, and then we blend in with very small amount in solution, and you can see it make a big change in the device characteristic. So if you look at the blue curve, at cast device, you have only about 1.8% efficiency, and if you go into 0.04 DIO processing device, and now you actually increase the device efficiency by a factor of 3. And the right-hand side shows the external quantum efficiency plot. And you can see the really different, if you see there are two peaks, the one at high wavelength at about 600 nanometer, and that is the photocurrent generated by our donor material, by the T1. And the peak at about 380 nanometer, and that the photocurrent usually generated by the PCBM. And from here, if you can see the device processed differently, the really different is the amount of photocurrent generated by T1 material. So next, when we see the difference in the device efficiency, we hypothesize that perhaps when we make the film differently, what really changed is the film morphology. So when we change the film morphology and actually change in the device performance. So now the question here is, how are we going to probe the film morphology different between the two devices? And the technique that we use to do this called grazing incident wide-angle X-ray scattering. Short name is GWAX. And in this particular technique, you have your blend, the Bohr heterojunction film. You shine X-ray at a very small angle, and you measure the scattering off from the surface of your film. And so this technique really measures the degree of film crystallinity or film order in the blend. And so this is the result from GWAX. So first, we prepare film with protein donor material, and that the plots show on the left-hand side of the slide. And so when you see a strong peak, the white peak appear there, which correspond to a strong diffraction peak, would mean that your film is quite ordered. And then when the right-hand side of the slide, I show the X-ray data for neat PC70BM. And you can see here, there are no real peak appear. So PCBM protein film is quite amorphous. So you see no diffraction, and you don't see any strong white peak. And now when we blend the two together, which is the ADCAS T1 PC70BM, and the second plot from the left-hand side, and you can see it amorphous. So what does it mean? It means when you add in PCBM, it interferes with the molecule packing, and therefore the blend film become amorphous. And now if you look at the film prepared with 0.4% DIO in the blend, and suddenly you can see the strong diffraction peak reappear. And the peak on the top, it corresponds to pi-pi stacking, and the one on the bottom corresponds to alkyl chain stacking. So what does it mean? The data tell us that when we blend the film and we process with 0.4% DIO, we improve crystallinity and order in the device. And because of that, you can actually see better photocurrent and also better device performance. We can also map out film morphology using transmission electron microscopy. And you can see the left-hand side for the ADCAS. You don't see any feature there. What really mean is that the donor and the acceptor, they blend really well. There are no contrast whatsoever. But if you go into the image on the right-hand side, which is 0.4% DIO process blend, and now you can see beautiful crystalline domain appear throughout the film. And so basically, it supports the degree well with our GWAC data that when you process with DIO, the film become more crystalline. And you can see the network structure have the domain about 20 to 30 nanometer in the width, and they all over the film. And you can see here, it also help us to understand why our device work better. So you have an optimal phase separation. You also have percolation pathway to transport the electron and hole out of the device. And so next, we also look at the internal structure of the film, because this data here I show you, basically the top, you transmit electron beam through the film, and so a lot of time people being skeptical about whether the internal structure or internal morphology of the film look the same as the top-down one. And to do that, we actually take our devices, we use focused ion beam, we actually cut the thin slide, and about 15 micron in the length and 5 micron in the width and 100 nanometer thick. So we transfer that slide, as you can see on the top right image, using the micro manipulator. We transfer that on TEM grid, and we look at the internal structure of the film. And here, I want you to focus on the ADCAS device and 0.4% DIO. If you see the right-hand side image, and the ADCAS, you see actually no contrast whatsoever, which is agree with the top-down TEM image I showed you earlier. And for the DIO process device, you can see the nanostructure fiber light throughout the film. So basically, the data really agree with what we shown you by the TEM from the top-down earlier. So now, again, when you see from TEM, it doesn't give you the clear domain side. You only visualize the one that actually form crystalline domain. The one that doesn't show crystalline, you cannot really visualize. So to really understand the domain side, the donor side and the acceptor side, and the width of that domain, we actually use resonance soft X-ray scattering technique. So what does the technique do? So basically, the donor have is actually absorption X-ray photon at certain energy, which is I show here in the bottom graph on the blue. And so we also look at the protein T1, which is the red curve, and it have absorption the X-ray at certain energy. So now we actually tune the X-ray absorption to those two energies so that we can obtain the contrast. And so the technique gives information about the domain size. It also gives information about the degree of mixing between our donor and the acceptor. And so now I show you the result from the X-ray. So I want you to focus on the right-hand side plot, top and bottom. So the red curve show the 0.4% DIO blend, and the domain size about 35 nanometer. It also agrees with the TEM data I showed you earlier. The ADCAS, because they blend very well, and the domain size a lot smaller, and the intensity of the peak also very weak. So that implies that the donor and the acceptor, they blend quite well together. And then the bottom graph shows you the relative phase purity. So in another word, it measures the degree of mixing of the donor and the acceptor. So the two red circles I show you there is for the ADCAS and 0.4% DIO process blend. And the ADCAS, so basically, again, the donor and the acceptor, they mix quite well, like I showed you through the TEM data earlier. But for the 0.4% DIO, the phase is quite pure. So you have protein donor and protein acceptor with very minimal mixing between the two domains. And now the question we ask, do the different morphology affect the charge recombination and therefore the fill factor in the two devices? And so before I go on, I want to highlight there are different loss processes happen in organic solar cells, and also happen in silicon solar cell or dye-sensitized solar cell or also perovskite solar cell. So you have similar type of losses. So when you have your material absorb the photon created excited state, which we call exciton, the exciton can also encounter trap. And if they get trapped, they're not going to go to the donor acceptor interface where they can do electron transfer. So for those that make it to the donor acceptor interface, and they do ultra-fast electron transfer, and if the electron and hole, they still strongly bound right across the interface, and which scientists also call charge transfer state. So if they sit there and they bound, there are higher probability for them to recombine and go back to the ground state. So this loss process people call geminate recombination. It means the electron-hole pair generate by the same photon event. And so they can recombine, and that process called geminate recombination. So what are the drawbacks of this? If you have strong geminate recombination, it competes with the charge generation process. So it means you have less free charge carrier formed in your device. So it's not good. So and then for those electrons that actually be able to transfer and form free carrier, and so basically there are two different types of loss process for this. One they call is basically trap-assisted recombination, and the second one is bimolecular recombination. So bimolecular recombination is recombination of free electron-hole pair together. They can fire each other after wandering around and recombine. And the trap-assisted recombination means if you have trap, and trap can be impurity, can be oxygen, water in your device, and this electron can get trapped and sit in the trap. And the hole move freely nearby, can feel the effect of the electron sitting in the trap, and they can recombine. So both of this type of recombination people call non-geminate recombination. It means that the recombination of electron hole that do not generate by the same photon event. And that the drawback of this type of loss is that now you can see your non-geminate recombination compete with the charge extraction. The stronger non-geminate recombination, there will be less free carrier present in your device. And so those are different type of losses. So now I will go through and try to understand in the two devices I showed you earlier, what type of loss present in the two devices, why they have different device performance. So before I go on, I just want to highlight briefly what exactly is field factor and how field factor can affect your current voltage curve in your solar cell. I show here the simulated device data showing how field factor can really affect your device characteristic. If you have the device with low field factor, the red curve, only 35%, and you can see you have only 5% power conversion efficiency. But if you can take that device, if you increase the field factor by a factor of 2, the green curve, and now you can easily double the device performance to 10%. And then if you increase even further to 85% field factor, you can reach easily 15% solar cell. And so now to really to probe the geminate recombination loss in our two devices, the technique that we use called time delay collection field experiment, and this is in collaboration with Dieter Neher in Germany. So in this device, we actually make the solar cell device, and then you apply a small bias in this device, with the idea here that if you have electron hole pair that is still bound to each other, you apply a small bias, you can actually separate them, okay? And so, and after that, we shine a short amount of, a short pole laser to our device. We wait for certain delay time, and we collect basically all the current generated by our device. And so basically, this tells you whether the voltage, the charge generation, it depends on the voltage or not. If the charge generation it depends strongly on the voltage that you apply, it means that the loss in your device is due to geminate recombination. If you see there are no voltage dependent, it means the loss is due to non-geminate recombination only. And so this is the type of data that we can collect by this method. So the right hand side where I plot the total charge generated by our device at CAS and DIO process. The right hand side of that plot shows germinate loss relative to the maximum photocurrent generated in our device. So you can see that the DIO process device doesn't matter what bias that you apply, you see the same amount of total charge. So what does it mean? It means that the charge generation process in this device doesn't depend on the voltage. It means there are no germinate recombination in the DIO process device. So if you look at the black curve, it shows the total amount of charge, but it strongly depends on the bias applied. So it means that the stronger applied bias, the more current that you can generate. So it would imply that the strong germinate recombination present in our device. And so basically the data show us this is the total type of loss in our device. So the right hand side for the DIO process device, you have only one type of loss, which is bimolecular recombination. On the left hand side for the ADCAS device, you actually have two different types of losses, and one is germinate recombination, and the second one is non-germinate or bimolecular recombination. And that's why you have two different loss mechanisms happen in the device. That's why you have lower short circuit current, lower fill factor, and therefore it impacts the device performance. You only have about 2.8% instead of 7% or so. So now we try to tie back these losses to the morphology. What exactly changed in the film morphology that give rise to very different type of losses? So if you look at the ADCAS blend, I told you earlier that donor acceptor, they blend so well. And also there is a certain degree of disorder or amorphous in the system. So what does it mean? It means that if you create the electron hole pair sitting at the donor acceptor interface, there are strong bound of the electron hole pair, very localized, and there's strong force hold them together. So that's why you need this additional electric field to pull them apart to form free carrier. But if you look at the DIO process film, it becomes more order. So what does it mean by it become more order? It means that you create electron hole pair, and now electron hole pair can delocalize on the larger unit, and because of the delocalization, and it's much easier to form free carrier, and you do not need the additional driving force of the electric field to form free carrier. So you can see here, it really depends on the local order of the donor and the acceptor domain that can impact the type of losses in the device. So this is kind of cartoon drawing show you that in the ADCAS film, you actually have amorphous and strongly mixed domain, and that's why they really affect the type of losses present. And on the right hand side where you have percolation pathway, quite order domain, you do not need to additional electric field to really separate the charge carrier. So this really helps explain how our device works. So now, how about a non-germinate recombination? Because what I show you the method to look at germinate recombination. What about non-germinate recombination? How do people study this? So for non-germinate recombination, I mentioned there are two different types. One is tripartite recombination. And the way that we study this, we actually take the solar cell device, we measure open circuit voltage at different light intensity, and then you make a plot of open circuit voltage versus light intensity, and you look at the slope of that line. So if the slope of that line equal to KT over Q, it tells you that the type of loss in your system is bimolecular recombination, which is the one I show on the right hand side. And then if the slope greater than KT over Q, it means you have trapped acidic recombination. But if you have a very pristine, very clean donor and acceptor material, you don't have impurity, and a lot of time you should not have trapped acidic recombination in the system. And that's what in our case here. So this is I plot open circuit voltage as a function of light intensity, and you can see the slope of both devices are close to 1. So it means that the only type of non-germinate recombination loss in the two devices is bimolecular recombination. So now the question here is, can we reduce bimolecular recombination with fast charge extraction? So the answer is yes, if you have very high charge carrier mobility. So to really understand about charge extraction and mobility in our system, we now go on and measure the mobility in our system. The way we measure the charge carrier mobility in our solar cell by fabricate electron-only diode, so where we sandwich our blend material between a pair of low work function electrodes. So when you do that, you ensure that electron is the only carrier injected into your device, and it will transport through the PCBM domain, and you measure electron transport. For hole transport, we fabricate hole-only diode, where we sandwich our blend between a pair of high work function metal electrodes. And a lot of time we use basically PDOT, PSAT, or capped with aluminum or gold. And when you do that, you ensure that the major transport or carrier in your device actually holds. So this is the type of data that you actually measure using this single carrier diode. We measure the current density as a function of voltage, and then we actually use the Mark-Gurney relationship to extract charge carrier mobility, and then this is the device result for that. So first, we also measure the transport in our printing donor material. We have the hole mobility about 5 × 10⁻⁴ centimeters square per volt per second. And the electron transport in the printing PCBM around 1 to 2 × 10⁻³ centimeters square per volt per second. So now when we blend the two compounds together, like I mentioned to you earlier, when you blend the two together in the ADCAS device, it becomes amorphous. And when it becomes amorphous, it reduces the hole mobility. You can see here both electron and hole mobility reduced compared to the printing material. But also very interesting that if you look at hole mobility and electron mobility for ADCAS device, it actually imbalanced. So the electron mobility, electron move faster in our solar cell than hole. So what is the implication of that? So if you have imbalanced charge transport in your device, so it means that one type of carrier was sitting around in the device longer, so therefore you increase the probability for them to recombine. And when you have stronger charge recombination, you can actually have lower field factor and therefore lower short circuit current and lower device performance. So now let us look at the device process with 0.4% DIO. So when you process, the film becomes more crystalline and it really impacts the hole mobility. So now you can see the hole mobility increase to 4.6 × 10⁻⁴, and it over 1 order of magnitude, and now electron and hole become more balanced. And as a result of that, we have higher field factor and also higher short circuit current and better device performance. So next we look at how the difference in morphology can affect the charge extraction. We see it impact recombination, it impacts the charge mobility, and let's take a look at the charge extraction. So to look at charge extraction, we plot the efficiency in another way. So basically, first measure the dark current, and then we measure the current under illumination, and then we subtract the dark current. So now what we look at the left-hand side curve is really truly the photocurrent density and a function of applied bias. The right-hand side plot, so now we plot the photocurrent density as a function of effective bias. It means the bias that allows it to extract carrier. So the driving force for charge extraction, basically. So now, what does the plot tell you? So if you look at here, if you look at how soon or how fast the photocurrent saturates at low bias, so if you see the saturation in photocurrent, so it means that the charge extraction is not a problem in the devices. And then you can also, if you look at the maximum photocurrent, it also gives you information about how efficient your device generates charge. So now this is the actual photocurrent for our two devices. So the first one I wanted to look at is the ADCAS device, the blue curve. So I showed you earlier the field factor at about 40%. And you can see that as you increase the effective bias, you continue to generate more and more photocurrent. So we never see the saturation current in the device. So what does it mean and how it is correlated to the morphology? So it means that in this device, you can have very high photocurrent. It means that you have no problem in generate the charge carrier. But the issue here is charge extraction. So you have the two donor acceptor blend quite well. When they blend quite well, and they also have little percolation pathway. So after you generate the carrier, it's difficult for the charge carrier to find a way out of the device. And the stronger applied bias you have, the stronger, the more current that you collect. And so basically, the morphology can really impact many things, and not just the charge generation, but also the charge recombination and transport, and therefore the device performance. So now let us look at the green curve, which is the device process with 0.4% DIO. So in this device, you can see the photocurrent saturated a very low applied bias. So what does it mean? It means that we have efficient charge generation, but we also have efficient charge extraction, because the electron and hole mobility are higher and they're quite balanced. So as the result of the morphology here, you have percolation pathway to transport carrier. You also have crystalline domain, and therefore you have higher mobility. And all of this can really impact the device performance. So with that, I would like to conclude that the solvent additive can be used to modulate the phase separation, basically the domain size, the degree of mixing between donor and the acceptor, and therefore it can directly impact the charge generation, charge transport, recombination, and extraction. What we found that high mix phase morphology in the ADCAS device, it leads to geminate and also high bimolecular recombination, and as a result, you have much lower device performance. And so to maximize the photocurrent and also the field factor, it is important to maximize phase purity. So you form pure donor and pure acceptor with very little mixing. You also want to get high mobility, you need to have structural order. You want crystalline domain. You also want small donor domain size so that you can maximize the charge generation. But also very important that you need sufficient conductive network to transport charge carrier out of your device. Because you can generate carrier, but there are no percolation network to transport them out the device, and then that can really impact your recombination and the short circuit current. And so what are the remaining challenges in solution process organic solar cell? And so one thing I want to point out that in terms of material design synthesis, we need some strategy. We also need theory to guide synthesis, because if you make a few compounds, it can take a long time for us to optimize the device. I show you today just one molecule. It took 3-4 students study that one molecule for 5 years to understand in depth how the device works and why it doesn't work, how to overcome certain type of recombination. And also to fabricate solar cell module using roll-to-roll coating or blade coating or inkjet printing, a lot of time you will require thick active layer. The device I show you today have the active layer about 100 nanometer. And so a lot of time for those technology, you will need about 200, 300 nanometer thick. And so to maintain high mobility, to get efficient charge transport, to have high efficiency, it's still a challenge. And that's why for a solar cell module, people can get about 6% and not 10 or 15 yet. And also we need to improve the device efficiency to above 10% for the module and also the device lifetime. And with that, I would like to acknowledge the collaborator, Guy Bazan, for synthesizing many compounds that we study in our group. And Michael Tony, we collaborate with him for the GWAC study. And Dieter Neher for the time delay collection experiment. And Harold Aide for the soft X-ray scattering method to look at degree of mixing. And this work is done by my student John Love and also Chris Proctor. And I would like to thank all the funding, Office of Naval Research, Mitsubishi Chemical Company, and also the Department of Energy. And also thank you very much for your attention.
Thank you very much for this informative lecture. And I think you covered the subject very well. Thank you. if there is any question for.
Okay, go ahead.
Actually, I have one question, please, if you.
Yes.
About the sequence of the dye, you said you prepared acceptor, donor. What is this sequence for? Do you want to drive the charge in one direction or what?
Actually, so the way that the approach that Guy Bazan used, the donor acceptor, so you make basically, because you donor acceptor type, you have intramolecular charge transfer state. And because of that, you can actually control the band gap of the material. So now the band gap can shift to longer wavelength, basically. So you control the optical band gap, and you can also manipulate the HOMO level, so you can control the open circuit voltage in the device.
Okay, thank you.
We have one question over here.
Yes, please.
Go for it. Oh, not? No. Okay, I think we're okay.
Is there any question here? Okay, thank you very much.
Thank you.
Sam.
Okay, next lecturer. Muna Mustafa Saeed.
She is
Muna
here.
is present.
Yes.
Okay, so please go ahead, Muna.
My talk is about production of novel, non-toxic, and red luminescent sensor based on europium-doped yttrium titanate co-doped into silica matrix for latent fingerprint detection. As we know, the fingerprint is an impression left by the finger, the ridges of the human finger or foot, which play an important role in forensic science to identify the offense. The fingerprints classified into two categories: visible fingerprint and latent fingerprint. Visible fingerprint result from contact of the finger with the semi-solid substance like clay or wax. And the latent fingerprint invisible, not clear, and can overlap with other fingerprints. So the trend of our research to enhance the visualization of the latent fingerprint. There are several methods for visualization of the latent fingerprint: optical, physical, chemical, and combination between them. But the most familiar method is a physical method, and the powdering is a most common method for visualization of the fingerprint, which depend on physical adhesion of powder to the fingerprint on the substrate. There are several types of powders: regular powder, metallic powder, and luminescent powder for identify the latent fingerprint. The regular powder successfully to detect the fingerprint from the smooth surface, non-tacky, such as glass, which consists of polymer for adhesion and dyes for as a colorant for contrast, such as mixture of ferric oxide, kaolin, and carbon. The metallic finger powder more effective for detection of fingerprint from rough and porous surfaces, but have several limitations which hazard to the user, which consist of meshed metal such as lead, aluminum, silver. So the limitation of conventional powder cannot visualize the fingerprint from difficult surfaces such as multicolor surface, and also a hazard for the user. Also, the particle size for the familiar fingerprints ranged in the microscale region, such as the silver powder, the particle size from 3 to several micrometer. So the luminescent powder is a new trend for visualization of the fingerprint, which based on luminescent nanomaterial which the luminescent nanomaterial can be excited by UV or blue light to give the emission color. The luminescent powder classified into luminescent powder based on organic compounds such as rhodamine, coumarin. This type of powder have several advantages such as low cost, excited with very low energy sources. But the limitation, the organic compound easily to degrade by continuous irradiation to the light, and also the emission spectra is very broad, so it does not give a monochromatic light. So our trend in our project to preparation of luminescent nanomaterial based on lanthanide metal ions such as europium, which characterized with pure red emission, terbium, pure green emission, and other metal ions such as samarium, praseodymium. The lanthanide characterized with sharp and high emission and also long decay time. The sensitization process for the lanthanide doped in any host, the host material can classify it into organic, such as 1,10-phenanthroline, or pure inorganic material, such as our matrix yttrium titanate co-doped into silica. This matrix excited by UV or blue light, and then transfer its energy into the emitting state of the lanthanide. As a consequence, the lanthanide gives the characteristic emission depend on the doping metal ion in visible region. This phenomena called down conversion, which absorb very low energy, high energy, and convert it into visible. Okay. Why nano powder based on lanthanide? Because the fine powder give high adhesion to the surface. In our project, we focused on preparation of nanomaterial, pure inorganic nanomaterial, doped into silica matrix, because silica matrix have several advantages that such as the cheap, easily to prepare, non-toxic, biocompatible, high doping concentration capability, and also for lanthanide especially, it gives unique photoluminescence properties such as long lifetime and high and stable photoluminescence emission color. Also, the silica can confine the doping material into the nanopore, which decreases the particle size of the pure inorganic material. So the main objective of our project, production of new green nano powder based on silica co-doped with lanthanide for latent fingerprint detection. This is our results. This is the XRD analysis for the europium doped yttrium titanate co-doped into silica, and we can see that the XRD pattern give a high crystalline percolor dispersed into silica at high calcination temperature 100 degrees centigrade. Also, the XRD analysis confirms that our particles size in the nanoscale, and also the TEM analysis confirm our results. The presence of europium ion can be confirmed using EDX analysis. And this is the emission spectra of the europium doping in our matrix, which give a highly monochromatic light, as we can see from the photo, due to the FF transition in the europium ion. And this is the photoluminescence lifetime decay curve. And as we can see from the analysis for calculation of the lifetime, that the lifetime is stable at from about 2 mole% doping to 52% mole%. Also, to apply our material in field, we should test the toxicity, and the LD50 for the high loading europium equals 6.2 gram per kilogram, which is a huge amount. So our material characterized by very low toxicity. We apply our material for detection of latent fingerprint from non-porous surface such as glass, transparent plastic bag with different color, blue and yellow. Also aluminum foil, scratched CD, and also we apply to the porous material such as green leaf paper, and we successfully determine or identify the details of latent fingerprint. Also, we apply our material for aged fingerprint for 7 days, which exposure to the air and the moisture, and also as we can see that the fingerprint is very clear. My conclusion, the prepared nanophosphor was successfully developing the latent fingerprint from difficult, non-porous and porous surfaces, and our materials is non-toxic. Finally, this work funded from the grant from the Egyptian Ministry of Scientific Research. So I thank my Egyptian ministry. And also I want to thank my Egyptian group, Dr. Magdi Sheb, Dr. Huda Hafiz, Asma Nabil, and my master student, Radwa Shukri. Also the Tunisian group under supervision Professor Ramzi Maliouch. And thank you for your attention.
Thank you. If there is any questions? Questions from the ladies section?
Yeah, I have question. Thank you very much for a very beautiful work. I have 2 questions. So you said that the material have high photoluminescent quantum yield. So what is the yield, PLU for this?
The what?
Quantum yield, photoluminescent quantum yield.
I measure that photoluminescence lifetime.
Not quantum yield.
Not
I
quantum
see.
yield.
And then the second, have you ever measured to see, because the photoluminescent quantum yield of rhodamine is quite high, right?
I know.
So I'm just curious, for your compound, how high is the yield, luminescent quantum yield?
In the future work, we will measure
okay.
this item.
Yeah. The second question is about how do you control the loading of your material into silica matrix?
How can I see this disperse it into silica?
Oh no, how do you control loading more and more of your compound into silicon?
We prepare this material using sol gel technique. So we can disperse a very huge loading concentration easily.
All right, thank you.
Thank you.
Any question?
Okay.
Thank you.
If there is no question, then our next speaker is Professor Ahmed Farfawzi Al-Hijazi.
Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. First of all, I would like to thank the organizing committee of the International Conference of the Applied Science. Also, I am pleasure to hear my talk about the antimicrobial activity of Chitosan with nanotechnology. In the last few years, the antibacterial and the multifactorial properties of the silver nanoparticle have received more attention. The antifungal activity of silver nanoparticle prepared by the modified Tollin process was evaluated in the pathogenic Candida species by means of the determination of minimal inhibitory concentration, minimal fungicidal concentration, and the time dependency of the yeast growth inhibition. The silver nanoparticle, the powerful nanoparticle against multi-drug resistant bacteria, is also all this put in the literatures in the different journals. The study revealed that the silver nanoparticle kill bacteria at such low concentration unit of milligram per liter, which do not reveal acute toxic effect on the human cell, but it is more effective against the pathogens. In the Physical Chemistry Journal, a one-step simple synthesis of silver colloidal nanoparticle with controllable size is presented. In this synthesis, reduction of the nanoparticles of the silver complex coated by the four saccharides as were performed: glucose as the monosaccharide glucose and galactose, and the average size distribution, morphology, structure, particle were determined by dynamic high scattering, transmission electron microscopy, and UV visible absorption spectroscopy. Thus, the using of the silver nanoparticle increased in the ratio of the surface, in the area, in the volume, surface active multi-center, and the surface reactivity, which lead to increase the number of the particle per unit area, and most importantly, the lower toxicity to the human being. So the silver nanoparticle elute silver ion, and it's well known that ionic silver has antibacterial properties. Thus, it is acceptable by eluting ions from the silver nanoparticle are responsible for at least the part of their antibacterial properties. The antibacterial effect of silver nanoparticle in the size and the shape are dependent, so the size of the nanoparticle implies in it has been the largest surface of area to come in contact with the bacterial cell, and hence it will have higher percentage of interaction than the bigger particles. In a review in other journals, since the several years ago, the great attention has been paid to the chitosan as a potential polysaccharides resources. So the production of chitosan is currently based in the carp and shrimp cell. The chitosan, it has unique biological properties, since they have non-toxic activity, biodegradable, and it is antibacterial activity toward the fungi and the bacteria and the viruses. So for this reason, chitosan is widely used mainly in different fields, including medicine, food, and chemical engineering, pharmaceutical preparations, nutrition, and agriculture. The antibacterial activity of chitosan has widely explored. The number of chitosan derivatives with the different modification has been prepared to improve the antibacterial activity. Chitosan has a strongly affinity toward the metal ion because the presence of the numerous amines and the hydroxyl group. The different metal chitosan complexes and the composition have been prepared to improve antibacterial activity as chitosan with the silver composite. The most common method producer of nanoparticle is the chemical reduction of the silver salt dissolved in water with a reduction compound such as citrate, glucose, hydroxine, and ascorbate. Production of the silver nanoparticle using chitosan as reducing, stabilized, and coating agent have been great antibacterial effect. So the aim of this investigation, the main purpose of this study is to investigate antibacterial activity, chitosan silver nanoparticle composite prepared by different silver nitrate, the structure, characterization, size, shape, size, distribution, surface, morphology, silver ion release,
will be investigated by using ultraviolet FTI spectroscopy, transmission electron microscopy, scanning electron microscopy, atom absorption spectroscopy methods. The Chitosan powder for our material is it is a practical grade, more or less 70%. It was purchased from Sigma, and the silver nitrate salt and acetic acid with an analytical grade. Also, the solution were prepared with deionized water. Preparation of Chitosan silver nanoparticle composite. It is prepared so the characterization characterized by the UV spectra. Also, FTIR spectra was obtained using various transform interfere instrument. Also, transmission electron microscope. The release time it is applied. So the bacterial strain in this project, the meaning using the different bacterial strain, either gram-positive or gram-negative strains. The gram-positive strains is Staphylococcus aureus, where the gram-negative bacteria, Pseudomonas aeruginosa and the E. coli, and these bacteria were kindly determined from the zoonotic disease of the National Research Center in Egypt. The antibacterial assay is determined by using the bacteria. This bacteria is cultured through the pros, and this is male in nourishment, and then subculture, and the silver Chitosan, it is isolated and prepared and making some dilution, so that the result is showing that the ultraviolet of absorption spectra of Chitosan silver nitrate composite prepared by different silver nitrate cis ratio. Also, ultraviolet spectroscopy, this is the figure for that, showing that the reaction, FTIR spectroscopy of this reaction, this is FTIR spectrophotometry also. This is by electron microscopy, transmission electron microscopy, the particles of the nano silver. Here you can see this particle, the dilutions or the ratio between the silver nitrate and the Chitosan from the different level. We observe it, and then scanning by the electron microscopy, but also the release of the silver ion were detected. The antibacterial activity using the turbidity test of the several bacterial strain, as I mentioned, that the bacteria from the gram-positive and the gram-negative, we show that in using the bacterial strain only, and this is antibiotic as a control, and this is silver nitrate solution against the different bacteria, and the different ratio of the Chitosan was observed. The concentration by microgram per ml of the different dilution, starting from the high dilution to the lower dilution, and the efficacy of the antimicrobial activity of different these pathogens was observed. There is more or less, we found that the antimicrobial activity of the different strain of the bacteria were effective, so that we can conclude that all obtained Chitosan nanoparticle composite sample showed initial burst within the first hour, followed by the gradual increase up to 12 hours in the reaction, plateau up to 36 hours. Chitosan nanoparticle with the silver composite showed the stronger antibacterial effect than its individual component, Chitosan and silver nitrate solution, toward the gram-positive and gram-negative bacteria. So this is the National Research Center, and we, all of us in National Research Center, open our heart and our hands to making the collaboration between all of you, and then we invite you to visit our country. Thank you for your attention. The second lecture I will be follow up by my colleague, Professor Dr. Inan. It must be done this procedure, but now because there is a relationship between the both lecture, I will be making the lecture, so that we also thank you for your invitation and thank the organizing committee. What we can call with the introduction, nanoparticle is a heterogeneous group of the substance with the various side one up to 100 nanometer, and the structures among the metallic nanoparticle server is most widely recognized of its application in the medical and other scientific field, including clinical diagnostic and therapy. The biological synthesis of nanoparticle will receive the considerable attention and offered many advantages. The various techniques, including chemical and physical properties, are developed to prepare several nanoparticles. We are used the milk from the milk of the camel and cows, because this is the economic material and highly protein in content, and this is all used widely to use, so that it can used as food additives, and show that this combination between the silver nitrate nanoparticles and the milk of the camel and cows, it is beneficial for our project. The milk is economic and easily available product, so they used for the synthesis of nanoparticles. The protein present in cow could be responsible for silver ion reduction. The control of the bacterial diseases is getting more difficult due to the growing resistance of the bacteria. This is a main project for main target, because the drugs now give the drug resistant against many of the pathogens, so we can shift this to making the treatment of such resistible bacteria. Meanwhile, the use of synthetic drug has severe effect and side effect in the body, so if you use the natural product like milk of the cow or the milk cow, you can use easily for eliminating of dangerous diseases. Therefore, it's useful for return of the natural product and the medicinal plant to overcome the side effect of chemicals. The current control measure of concentrated mostly in the preventing dissemination of the disease to uninfected animal and human by using natural product. Therefore, it is useful to return to the natural product and the medicinal plant to overcome the side effect of these chemicals. The application of nanoparticle focused on the control of the diseases. Silver nanoparticle in the particular exhibit different activities, including virucidal, antibacterial, bactericidal, antifungal. Thus, the objective of the present study was biosynthesis of nanoparticles using cow milk and camel milk to evaluate the antibacterial activity of the synthesized silver nanoparticle in vitro. The material of method, the silver nitrate are obtained from the sigma, also the cat and the camel milk is purchased from the market. We are using all this material, making the shaking, mixing with the silver nitrate. The reduction of the silver ion in the reaction mixture was monitored by the change in the color of the reaction mixture from the milk white to the dark brown. The reduction product is spread by centrifugation at 13,000 RPM for 15 minutes and purified by dispersion of the pellet in the autoclave water. The process of the centrifugation and dispersion were repeated several times, ensure the pellet separation of the free intervals from the silver nanoparticle. The obtained nanoparticle was freeze-dried minus 80 centigrade and used for the characterization of the study. Autoclaved water was used. The ultraviolet spectra were performed Also, the FTIR spectrum is obtained, electron microscopy and X-ray was obtained. The bacterial strain, here we're making a lot of bacterial strain for the gram-positive Staphylococcus aureus, also Streptococcus pyogenes, the gram-negative Klebsiella pneumoniae, Pseudomonas aeruginosa, Salmonella typhimurium, E. coli also used. The pathogenic bacterial strain was used to determine antibacterial activity of silver nanoparticle conjugated with the milk of the cow and camel. So the bacterial is used for the propagation of the bacteria, and the adding of this material prepared, we found making to evaluate the inhibition of this bacterial growth. Also, for this examination, we are making the statistical analysis. We are forming the following result. We can show that the zone of inhibition of the different pathogenic bacteria of the Staphylococcus or Streptococcus as a gram-positive or Klebsiella or Pseudomonas, Salmonella typhimurium or E. coli, we found that there is the great attention, the efficacy of the different concentration of the material. We have found the controlled bacterial growth, the milk and the cow milk or the camel milk. It is found that the more effective, the cow milk, it is more effective or higher, all the both have an inhibition, but the more pronounced in the for the cow, for Staphylococcus and Streptococcus, while the camel, it is more effective in the Pseudomonas aeruginosa and E. coli, and both of these pathogen is very dangerous for the human and the animal. So this material prepared give us a good availability to making the reduction of the different pathogenic bacteria which are affecting either infected human or animal, so that the good opportunity or a chance to find the new material like of the silver nanoparticle conjugated with the cow milk or the camel milk to protect us against this hazardable bacterial strain. So we thanks for you for your attention and open our collaboration, and thank you again for your attention.
When you go back to the slide that you're comparing with antibacterial cold milk silver nanoparticle with the camel milk silver nanoparticle?
Yeah.
So what are the statistical differences and statistical significance?
There is the great scientific difference between these bacteria, as we show that in the picture. We found the good efficacy of these pathogens and statistically significant by using the Duncan test. So
basically, I'm asking what is the p-value?
T-value, yeah, two tail.
Less than 0.05, because when I look at it,
Yeah.
all the bars are level.
The bars, you found that the bar, it is fluctuating and have a good significance difference between the both reaction. Thank you.
Okay, thank you.
Thank you.
Now we can break for the coffee break and come back. Thank you.
Thank you.